Alright, are we live? Could you guys give an indication in the chat? Leave a like, comment, subscribe, all that good stuff. We'll be doing even more math in the days ahead. Alright, okay. Welcome everyone to the live stream for our differential equations test. Of course, in the school in which I'm teaching, this is the third level of the mathematics series. So there are 3 levels of mathematics in this Polytechnic, and we're doing the third level. Today we're going to be attempting the midterm test, and it's going to be an interesting one. If you want to join along in doing this test, the questions are in the description box below, so you can check that out. And if you enjoyed this video, remember to like, comment, subscribe, do all that good stuff. It really helps out with this channel. Alright, so we're going to now solve. Our first question is to solve this particular differential equation. It looks a bit like this. And the strategy we're going to adopt is to bring all the letters that are the same in one side. Yo, One John, welcome back. I love his O-level videos. You should check out these O-level recaps. It's really amazing. So we're going to put the x's all on one side and the y's all on the other side. So the approach in which we're going to do this is to do this cross multiplication. Yes, this should feel like memories. There are some similarities between the differential equations here and in university. So we're going to do a cross multiplication, and we're going to be left with cosine of x dx. I always like to tell my students that this is mathematically imprecise. Of course, you can debate that, but we're going to take integrals on both sides, and this way mathematicians are not going to get angry at us when we do this. Well, it's weird because this is coming from a potential mathematician. Okay, and what we now need to do is to integrate these expressions. So we're going to take this expression and integrate it with respect to y. And the way we're going to do that, well, integrating y gives us half of y squared, and integrating 1 gives us y. And finally, we're going to integrate cosine of x, which gives us sine of x. Of course, if we stop here, it's going to be a little bit challenging, so we need a plus c. There are going to be some Laplace transforms later on in the paper, so these are useful tools in helping us solve differential equations. But for now, we're just warming up in the process. Of course, we want to be really fast when we solve these questions because time is of the essence. We only have 1 hour for this paper. So that's our first question. And for the next question, we're going to solve this differential equation. At first glance, this equation might look rather challenging, but there is a relatively straightforward approach to solve this. In fact, we could do the derivations, but in the interest of the exam, all we need to know is that we can call this particular expression, or more precisely, the thing in front of the y, we can call this the p of x term, and this can be the q of x term. Now, why are these terms useful for us? Well, these terms are going to help us obtain our final answer. Okay, so what that looks like is a few steps, requires a few steps. The first step is to calculate what we call the integrating factor, which looks like ix. This will be the exponential of the integral of px. Alright, just to bring everybody up to date. And in this context, px here refers to the function 2. It's just whatever is in front of the y over here. Perhaps I should write this more precisely, more cleanly. And we are going to integrate 2. Well, that just simply gives us 2x. There is no need for plus c, and if you want a technical reason why that's the case, let me know in the comments section below. Now with the integrating factor, we are now ready to write out the general solution, which looks a bit like y times I of x equals the integral of ix times qx. With this integral, well, all we need to do is to plug in each of these terms. So I'm going to plug in ix with e to the 2x and qx with e to the minus 2x. Some of you might notice there was potentially a faster solution to this question, and if you are confident in doing that, go for it. However, this is a perfectly valid solution nonetheless. If you're wondering what's with the hoarse voice, honestly, I have no idea. Maybe the mic sucks, maybe my voice sucks, who knows? We'll find out. Or maybe it's you, I don't know. Now, so, well, you take exponential, e to the 2x, multiplied by e to the minus 2x. The powers would cancel out, and you're left with e to the 0, which is just 1. So this simplifies to just 1. And what's the integral of x? Well, that's just simply x plus c. Now, there is the plus c over here. You need the plus c here, even though you don't need it here. Again, for a technical reason why, let me know in the comments section below. Finally, since we have the option to do so, let's perhaps isolate the letter y to very cleanly answer our question, which is, which looks a bit like this. Maybe I should not write it over there. Let me just scroll down. Much better. There we go. And that is the linear differential equation. That's how we solve this equation. Relatively straightforward content as far as we're concerned. Alright, for the next question, yes, our axolotl friend has indicated that we are encountering a Laplace transform question. Now this question, this year is in the Polytechnic in which I teach, is the second year. Right, so this is what we call EMath 3, which covers fundamentally differential equations rather than, which requires us to use the previous levels of mathematics to solve. So we are now going to compute the Laplace transform of this particular function. There are multiple ways to denote this, but this works just as well. The approach in which I've taught my students to do this is to use the math table and copy its values. I might be able to recall that. I think I can recall it, but just give me a moment. But before we do that, we need to do some splitting. Now, thankfully, the Laplace transform is linear, which allows us to actually split up the plus terms. Whoops. It's the same property that we can apply using differential equations. Yes, we do have a table, so you do not need to memorize this. You can even Google it if you wish, but I'm going to try to remember because I've been teaching this for the past few lessons. Now, for linearity, we can even pull out the constants, so it looks a bit like this. And now, just like what our axolotl friend has indicated, we are going to use a table of values to calculate these guys. If my memory serves me correct, the function 1 has the Laplace transform of 1 over s. T to the n is given by n factorial over s to the n plus 1. I believe this works. I genuinely think this works. I believe the sine of 2t, or sine of at, becomes a over a squared plus, s squared plus a squared. And the exponential will become 1 over s minus a. I believe these are the values. You can go check that out in the table. And so we can apply each of these expressions. In fact, I'm going to first write out the template and then copy out each of these expressions. We need to contextualize with the correct value of a. In the second term, a equals to 5, so we're going to replace this a with 5. In this case, this is going to be 2. This a here is going to be 2, so we're going to replace all the instances of a with 2. And finally, this is t cubed, so this is a 3 over here. We're going to use n equals to 3 to obtain 3 factorial over s to the 3 plus 1. Of course, we can simplify all of this, and there's no need to memorize any of this. You can refer to the math table that is given in the actual test. This would be 3 over s. Oops, typo error right there. 1 over s minus 5. Whoops. Minus 2 over s squared plus 4. And 3 factorial is 3 times 2 times 1, so that's 6. 6 over s to the 4. You are right, there is in fact a table, and in fact the table goes in the reverse direction, which leads us to our next question. Our next question is going to be the inverse Laplace of these functions, which takes a little bit of time to calculate, but just a little bit. It's not as complicated as it seems. Just like before, we can do some splitting, and we can even pull out constant multiples. We call this the linearity property. If you want to learn more about that, I have a video on what is a linear transformation. Really, I'm going to write it in this way because we can use some properties later on. In fact, for this term over here, I'm going to purposely write it as, I'm going to purposely write this as 2 factorial over s to the 2 plus 1. Because if we were to refer to a list of Laplace transforms, we're going to see that, well, 1 over s minus a is obtained via e to the at. So in fact, that gives us the first Laplace, the first inverse Laplace. If taking Laplace transforms goes in this direction, then taking the inverse Laplace goes in the reverse direction. So we're going to replace a with 2 and obtain e, we're going to obtain e to the 2t. For this term over here, the math table actually tells us we obtain this from cosine of at. So this is going to be the cosine of, in this case, a equals to 2. This is the cosine of 2t. This one over here comes from t to the n. Alright, so this will be t, well not t, sorry, this will be n factorial over s to the n plus 1. And as you can see here, n equals to 2, so we're going to replace n with, 2. And finally, this last one over here, I'll let you guys check it out as an exercise. Or you could think of it as a derivation from this term as well. There's actually some connections you can make over there. This is going to come from the constant function. This is going to come from the constant function. My brother and his church mates are having some cell group today, so it's a little bit noisy, but we can handle that. Now, if you're wondering why the speed of the questions are really fast, it's because we don't have a lot of time. We only have 1 hour to complete this paper, and usually the last question takes up the most amount of effort. And so we're going to be very judicious about the time that we can spend on these questions. Alright, so this is all raw, by the way. I've not prepared this beforehand. I did not come in with an answer key. I did not look at the paper. This is completely blind, so this is gonna be fun. Alright, for this next question, we have a few parts. Right, so for part A, we need to solve this particular differential equation. Okay, now to solve this differential equation, you may have remembered the technique, you might have forgotten it. In either case, we will first write this using what we call denotation. So I like to think of y double prime as differentiating this 2 times. Alright, y prime as differentiating once, and y as well differentiating nothing. So you can think of this as d squared minus 2d plus 1 of y. There is a rigorous way to justify this approach, although this is rather challenging, but there is a way to justify this calculation in this notation. It might be a bit foreign to some of you, but it's fine. It's not a big deal. The key point over here is to replace all the d's with m's and then solve for m. Now you can use the quadratic formula for this. You can complete the square, or you can remember some of your algebraic identities that tells you that this equals to m minus 1 squared equals to 0. This is EMath 3. This is EMath 3. So m minus 1 all squared equals 0, and therefore m equals to 1. Based on my memory, which I'm relying on because I do not have any math tables with me, I believe this falls under one of the equations that tells us that the general solution, we call it yc, is given by c1x plus c2 of e to the x. Alright, take care, mate. Take care, Lucas. I have the EMath 1 stream. It's on the channel. You can go check that out if you wish. It's in the live streams. You can go and take a look there. Alright, so I believe this is the solution. I believe this is the YC solution. In fact, I will call this YC first because that will help us later on with the differential equation. Okay, so now in part B, we need to evaluate this particular computation, which again, if you've not seen this notation before, it does take a bit of effort to decipher what's going on. Let me know if you want me to do a full video on that in the comment section below, but we're just gonna run with it according to how we are going to test it in the examinations. So here's the idea, right? We're going to try to use one of the formulas to help us. Now, in general, as much as I can, if I recall correctly, this is an exponential term. So the number over here, the coefficient in front of the x, right, is 1. So for exponential terms, the rule of thumb is to replace all of the d's with this value. Let's check. So let's calculate 1 squared minus 2d, minus 2 times 1 plus 1. Well, this simplifies to 0. And if this simplifies to 0, we can't just substitute this value. We need to use a different formula. Now I remember which formula this is because I have been teaching this class since the start of this semester. But for those who are unfamiliar, you need to use the 4th rule in your formula table. For those of you who are not in the Polytechnic, don't worry about it, just enjoy the process, it's gonna be fine. This is actually the shortcut version of the method of undetermined coefficients. Let me know if you want a video on that in the comment section below. So we're going to use a formula that basically says we need to pull out, we need to pull out this exponential term and, and we still need to keep all of this, but we need to make a few modifications. So we need to write this as something squared minus something plus 1. Perhaps I can give us a little bit more space here. What do we need to replace this with? We need to replace every instance of d with d plus k. Of course, in this context, k equals to 1. So we can do a quick algebraic expansion. Now, some of you might have noticed that there was a shorter way to do this. Let me know what that shorter way is in the comment section. In the chat, you can shout out what the shorter way might be. But for those who have no idea what's going on, let's first complete the calculation here. And let's do this slowly. So this is d plus 1 all squared. That's d squared plus 2d plus 1. This is minus 2d minus 2. And this is plus 1. So you're gonna notice that a bunch of things would start cancelling out. You are actually simply left with d squared. So this simplifies to ex 1 over d squared of 1. In fact, I'm not going to write this as d squared. I'm going to write this as 1 over d of 1 over d of 1. When we use the notation 1 over d, we're basically asking the question, we want to reverse differentiation. Well, what is reverse of differentiation? What's the reverse? Well, there are some technical names for it, but simply put, the reverse of differentiation is integration. So let's integrate 1, that's just x. You might be wondering, do we actually need the plus c in this context? The answer is no. The answer is you do not need the plus c. You can include it if you wish. There is no need for the plus c. Again, for the technical reason why, you can feel free to let me know in the comments section below. We need to integrate x because we have a 1 over d expression over here. So that means we need to integrate x to get x squared over 2, which simplifies to half of x squared e to the x. So the key trick is to use the correct formula, complete the calculations, and recognize that 1 over d corresponds to integration. That's going to help us with the next part. In fact, these two portions here are going to help us with the next part. So part C asks this question, right? We need to hence, or in this case, the math term I like to use is deduce the solution to this particular differential equation. Now, how do we solve differential equations in general? Well, we can approach this by first using d notation. That really helps us quite a bit. And actually, we can do one more thing with this notation, right? We can split this up into two smaller equations. So the first equation is d squared minus 2d plus 1 yc equals to 0. The other equation is to replace the y with yp. Our final solution is going to be of the form yp plus yc. And hopefully this doesn't take us too much time or effort. So we need to solve this differential equation and this differential equation and then piece them all together. Again, there's a very beautiful theory as to why this works. You can let me know in the comment section below if you are interested in that. Yes, I'm a math nerd, even though this is a course for engineers, but that's that. I have no idea what's happening up there. You guys hear that sound, right? It's probably not in my room. This is really disturbing. This is very, very disturbing. I have no idea what's happening. Okay. Okay, I think we're good to go. Okay, hopefully the noise is not too annoying. We can continue on with the question. So this thing over here, we've actually solved this equation just now. This is actually the solution to our part A, which is given by c1 times x plus c2 times e to the x. So that's kind of the first part of the solution, which we are going to substitute eventually. However, more importantly, we need to calculate the solution to this particular expression. So the key trick here is to apply the inverse D operator on both sides. It sounds a little dodgy and sketchy, and if it's the first time you're seeing this, it is kind of dodgy and sketchy. But you can trust that this is actually a legit operation. If you are doubtful, let me know in the comment section below. Now, the key trick over here, one really important trick, is the fact that this guy has the same linearity property as Laplace transforms, as differentiation, as integration, and just like the inverse Laplace as well. This transformation is linear. So linear algebra plays a crucial role in differential equations. I believe our ex-Lotto friend who did university would agree with that. So we can actually basically, when I said that this is a linear transformation, basically we can split up the plus in a nutshell. And in fact, we can write this in two terms. So we can maybe call this can be term A, and this will be term B. Okay? Maybe I'll call this not term A and term B, but I'll call this maybe term 1 and term 2. So we're going to calculate each of these terms. Now, term 1 is, I think I made an error. This should be positive x. So for term 1, we're going to calculate this expression. And in this context, k equals to minus 1. So let's just check that we can plug it in. We're going to get 1 plus 2 plus 1. Yes, and that would give us 4. So it's not a zero term, which means we are able to just substitute all of the d terms with minus 1. The whole answer, the whole expression would simplify to the number 4. So that's for the first term. For the second term, we've actually calculated this just now. With a little bit of effort, we actually obtained that the second term is half times x squared e to the x. You can refer to that calculation. We actually did it right here. Right? This is 1 over d squared minus 2d plus 1. This is also 1 over d squared minus 2d plus 1. This is e to the x. This is e to the x as well. Therefore, we're using this solution. So it's a really, that's how we solve this equation, but that's to obtain yp. So as I always tell my students, you need to answer the question by actually writing the final answer out. This is yp, this yp, plus yc. yp plus yc. It's a little bit tedious, but it gets the job done. Alright, let's go for the next question, which involves some Laplace transforms yet again. So here's how we're going to do it. So for the next question, this coming question involves Laplace transforms. We need to calculate the Laplace transform of e to the t with the convolution of t. So this is the convolution operator. It has a rather technical definition, which I can write down and I can prove some things about it. It's actually really useful in probability theory. But the important thing to know is that the Laplace transform of a convolution is the product of Laplace transforms. That's one of the few things that Laplace transforms can do, which really does set it apart from other kinds of calculations. Now the Laplace transform of the exponential is 1 over s minus k. This is k equals to 1 in this context. And this is t to the power of 1. So the Laplace transform of that is 1 factorial over s to the 1 plus 1. All of that would simplify to 1 over s squared. And we can actually combine the fractions because it looks a little bit more pleasant. It's not the most necessary thing to do, but it works. This works. I can even tell you the Marx composition, but I'm not going to do that. Alright, so that's part A, and for part B, for the next part, we need to evaluate this calculation. We need to calculate the inverse Laplace transform of this expression, which looks horrible, but we are given a hint. The key is to write this as a sum of partial fractions, and this is how we are going to do it. Now we have two factors, just two, no powers or whatever, so it's just two factors. These are quadratic factors. These are quadratic factors, which means that the numerator needs to be of the form a polynomial with degree 1. The highest power here is 1. If this is 3, then you should get a quadratic, and so on and so forth. And at this point in time, we could do the partial fractions. We actually can. I'm not gonna do that. I'm not gonna do that now because I'm gonna cheat a little bit. We're gonna do a bit of splitting, and we're gonna split this up in a really careful manner. The first observation is that 4 is written as 2 squared. So that's gonna play a crucial role for us, right? 4 is basically 2 squared. And because 4 is 2 squared, I'm going to purposefully put a 2 here and divide it out, which will come in handy later on. For the next decomposition, it's the same idea. This will be c times s divided by s squared plus 3 squared. Maybe I can make some space for us. Finally, the last term is going to be d divided by, the last term is going to be d divided by 3 multiplied by 3 divided by s squared plus 3 squared. And some of you are wondering, what on earth am I doing with this calculation? Why do we care? Why on earth do we even bother? Well, the reason is because we can actually take the Laplace inverse right away. we can actually take the Laplace inverse right away. On the left hand side, we're going to take the Laplace inverse, the Laplace inverse of the entire fraction, which is what the question is asking us to do, right? We can do that. On the right hand side, we can actually take the Laplace transforms of each of these terms. The inverse Laplace transforms of each of these terms, and I'm going to let you check that using the math table, we're going to get the cosine of 2t, the sine of 2t, the cosine of t, and the sine, made a typo there, the cosine of 3t, and the sine, this is the d, let me write that more properly, of 3 times t. And that is the Laplace, I don't know how to pronounce this, the inverse Laplace transform. That is really the answer, and you would get some partial credit for this calculation. Now you won't get full credit because we actually still need to go ahead to calculate what A, B, C, and D are. For the astute among you, you realize that there's going to be some equation solving involved, which is going to involve some linear algebra. Right? Linear algebra really plays a crucial role in all of these calculations. So let's do that. Let me rewrite all of that on the bottom. All that remains in this question is to calculate what A, B, C, and D are. And to do that, in fact, I'm just going to put that because once we have the numbers, we can write our final answer over here, right? In fact, we can even prepare our final answer right away. This is not the final answer yet, but once we've calculated these numbers, we are good to go. Okay, so here's the idea. Let's cross multiply on both sides because that's how we compute partial fractions. On the left side, the denominator is clear. On the right side, we get that calculation over there. Essentially, we have multiplied this expression on both sides. So when this fraction multiplies with this term, the s squared plus 4's cancel out, and we have an excess of s squared plus 9. You can approach the similar idea with this part over here. So what do we need to do? Well, let's just expand this term. This will be as cubed. Right, so let's just write it this way. This will be as cubed. This will be 9as. In fact, I'm not going to do it this way. I'm going to do the bs squared first. Then we're going to go 9as. Then we're going to go to do 9b. Let's do a similar calculation over here. The reason why I'm arranging it this way is because it does make our life a little bit easier, right? Just give it time to stew. All right, let me cook here for a while. There we go. We have these terms like this. And now we observe something really important. How many s cubed terms are there? There are none. This is a plus c s cubed terms, but there are none. What we can conclude from this, let me zoom out a bit. What we can conclude is that the total number of s cubed terms is 0. There are no s cubed terms over here. But what about the s squared terms? There are no s squared terms as well. So the s squared terms, b plus d, add up to 0. this part over here, we have 9a plus 4c. So we have 9a plus 4c s terms. This equals to how many s's? Oh, just one, right? So it's just one over there. And what about the constant terms? Well, the constant terms, 9b and 4d, they add up to 1. And so 9b plus 4d equals to 1. All that remains is to do a little bit of simultaneous equations to obtain a, c, b, and d. And I'm going to let you try to figure this out yourself. But I believe, based on my superpowers of mental mathematics, a should be equal to 1 over 5. Which means c must be negative of 1 over 5. And I believe b and d has the same effect. 1 over 5 and minus 1 over 5. I think I might have made... Did I make an error here? Did I make a careless error here? No, I think we're good. I think this calculation looks fine. Yeah, this calculation looks alright. Although I'm kind of suspicious, because part of me is thinking the answers are a bit too good to be true. Let me just stare at my work here for a brief moment. Yeah, this looks fine, because I think s plus 1 works out nicely. So we have the values of a, b, c, and d, which means we can plug that into our expansions over here. And the answer is going to be 1 over 5, that's our a term. We need to take b divided by 2, so that's 1 over 10. We're going to just keep c on its own. And we need to divide d by 3, so that's negative 1 over 15. We can remove the excess plus signs where necessary. And this is the answer to our question. The goal was to calculate the Laplace inverse. So what we did here is to decompose this fraction into two parts. Apply the Laplace transforms, Laplace. I don't know how to pronounce this word. Laplace. Let me know what you think in the comment section below. It's gonna be cool, right? So all that remains was to actually calculate these constants, which we did by comparing coefficients and then solving it. If you've done a little bit of linear algebra, this should feel a little bit like linear algebra. For everyone doing the math module in the Polytechnic, please go and learn linear algebra. It's going to be really useful for you. Trust me. And that leaves us with 17 minutes for our final question, which looks absolutely horrible. Not a fan. I kind of spent a bit more time than I should have, but let's just temper ourselves here. Let's solve this differential equation. So let's solve this differential equation. Now this equation looks absolutely horrible, and you might struggle with this for a while. I don't know if my student actually solved this equation the other time. I'm not too sure. But at first glance, it seems like it's not a very easy equation to work with. However, you might think to yourself, okay, there's a bunch of x's and y's and it looks pretty horrible. But what if we were to do a bit of flipping? The idea is that the x over there at the bottom feels a little bit difficult to work with. In fact, the whole denominator on the bottom over here is pretty horrible. So let's just flip it to the top. Hopefully we make some progress from this. And it turns out we do. We do actually make progress from this because we get a bit of cancellation. Now, of course, we need to cancel things carefully. This is e to the y minus x over y. Alright, that's how we do the cancellations. And some of you might realize that we actually can solve this equation right away. So the trick here, right, is to bring this term over to the side. The idea is that we want to write this not just as x over y, but as 1 over y times x. And you might realize from this calculation that this is going to be the term p of y, and this will be the term q of y. This is our first order linear differential equations using the method of integrating factors. Yeah, we're back to integrating factors. Okay, so to calculate the integrating factor, this is the e, the exponential of the integral of p of y dy. This simplifies to the exponential of 1 over y, of the exponential of the integral of 1 over y. And this simplifies to the exponential. Well, the integral of 1 over y is the logarithm of y. You always need to have your modulus symbols unless the question specifies a particular value of y. In this case, y is positive, and that means we are pretty safe. Our calculation works. We can remove the modulus symbols. What that means is that the exponential and the logarithm terms cancel out, and we're left with y. This is from eMath 1. And once we have that, we can actually write down our final answer, which is a little bit annoying in terms of notation, but it's not as bad as it seems. Looks a bit like this. Now, the integrating factor, that's I of y, that's x. Well, I of y is just y. And q of y is e to the y. I think I made a typo here. This should be a y. And the q y term is e to the y. So that requires us to integrate y times e to the y. I don't know if you guys remember, but we have a technique to integrate a product of two functions. There's the reverse product rule, also known as integration by parts. So this is my approach to do integration by parts. It's similar to black pen, red pen's DI method, but I call this the ISID approach. Whoops, not enough space. Let me get more space here. This is the ISID approach. Now, how do you use the ISID approach? Well, once again, you ask yourself which term is more easily differentiated. Well, if you differentiate y, you just get 1. Oops, camera's right there, 1. Right? And if you differentiate e to the y, you get e to the y. And it's kind of more complicated. So we're going to differentiate this guy. We're going to integrate e to the y. So what's the integral of e to the y? Well, integrating an exponential is basically just the exponential. And so we can just plug that in over here. I made an error. This should not be x, this should be y, because we are working in y. Well, what about this term? Well, s means we keep it the same. So I'm just going to copy and paste that. And what's d? D is differentiation. So how do we differentiate? Oh, darn it. How do we differentiate y? That's just 1, right? This is 1, so we can just write 1 over here. This is our technique called integration by parts. So that simplifies to y times e to the y, subtracted by the integral of e to the y. But the integral of e to the y is simply just e to the y. Remember your plus c. We still need a plus c. And actually, the question requires us to express this in terms of y, but since there isn't any straightforward way to do this, this is our final answer and it works out just as well. In fact, if you want to make y the subject, you might need to use this thing called the Lambert W function. I don't actually have a video on it. Honestly, I'm not too impressed by the W function. I know a lot of YouTubers and my good friend Anthony from the Paratutor likes to use W functions, but I don't know, it just doesn't really excite me as much. So there's that. Now with 10 minutes to spare, you can actually go ahead to check your work. You can try. But time is of the essence. Well, but we managed to finish this in less than an hour, and I believe this should net us full credit. I believe this will get full credit. The solutions are left as an exercise. You can go to GeoGebra, Wolfram Alpha. You can ask your math nerd friends to solve this and see if they get the same answers. And that is my attempt of this paper. So that's it. That's it for this stream. And I will catch you guys when I catch you guys, probably at the end of the semester when we actually do the full 2-hour paper. Remember to like, comment, and subscribe for more awesome videos to come. I'll catch you guys soon.